All right, so Kw equals our concentration H plus times OH minus. Again, we could use this to compare the H plus concentration, which is the acid concentration, to the OH minus, which is the base concentration. Whichever one's larger will tell you if it's acidic, basic. Obviously, if they're equal to each other, we're looking at neutral in that situation. We have the pH is equal to minus the log of the H plus. To calculate the pH, remember the pH scale runs from 0 to 7 to 14. Less than 7 is acidic, greater than 7 is basic, and 7 on the nose there is neutral. We saw a similar scale, which is the pOH, and that is minus the log of the OH minus concentration. Again, they do tell you kind of what you need. pH, you need the H plus concentration. pOH, you need the OH minus concentration. Now, the nice relationship between those two is if you take the pH plus the pOH, it will equal 14. So if you are given the OH minus concentration and want the pH, you can calculate the pOH and then just subtract 14 to get you there. We also talked about that if you do have the pH given to you, you could directly get the H plus concentration from that by taking the inverse log of the negative pH. Again, on most people's calculators, when you do the inverse log, which is typically the shift or second button, a usual pop up like a 10 and a caret, and then you want to make sure you make the pH there negative. Similar, if you're given the pOH, you could get the OH minus directly from it, which again would get you pretty identical calculation there. The inverse log of the negative pOH. And once again, that kind of looks like a 10 and a caret and negative pOH. So as we talked about last time, as we did, it does give you a variety of options in terms of how to calculate some of these things. You may never even need to use kW. You can still use kW if you wanted to, instead of maybe inverse logging. Does give you a variety of ways to calculate things like pH and pOH. Any questions on any of that there? All right. So next we're going to talk about our electrolytes and strong electrolytes and weak electrolytes. As you may remember from 200A, strong electrolytes are things that 100% break apart, sometimes referred to as being dissociated into ions. Because they break apart into ions in solution, those ions help conduct electricity, so they conduct electricity very well. So a strong electrolyte will, like, for example, if you had electrodes attached to a light bulb and you put it into a strong electrolyte, it would go off and be very, very bright, the light bulb, because it's conducting electricity very well. And that's because, for example, put some salt, or you have salt water in solution, you have 100% of these ions. So you have nothing but sodium ions, chloride ions floating around. You have none of the whole units sealed together. And because the presence of so many ions in solution, that's definitely what helps conduct electricity. A weak electrolyte, on the other hand, is something that is not completely dissociated. In fact, a weak electrolyte mainly stays together, but will still break apart into some ions. This is acetic acid, which is a weak acid and a weak electrolyte. And it will mainly stay together in solution as acetic acid, but will break apart into a few of these ions. So if you looked at sort of a beaker of that, you're going to mainly have your acetic acid kind of sealed together, but you will have a few of the acetate ions floating around and some H pluses floating around. So because it's able to still conduct a little bit of ions in that solution, it's still able to conduct electricity. It would not be able to conduct electricity anywhere near like a strong electrolyte would, but it still has that ability to do so. So acids and bases can be strong acids or weak acids, or strong bases or weak bases, which means they are also strong electrolytes or weak electrolytes. So when we talk about strong acids, there is sort of a list of some common strong acids, which is really a good list to know. And because of this list, you can kind of use it more as a maybe process of elimination. If it's not an acid on this list, you could probably make a pretty safe assumption that it's going to be a weak acid. So strong acids are our hydrochloric acid, our nitric acid, our perchloric acid, our sulfuric acid, our hydrobromic acid, and our hydriodic acid. So this sort of list of 6 strong acids, like I said before, is a pretty good list to know because in most cases, like I said, you could kind of use as a process of elimination. Again, if the acid you're looking at is not one of these 6, you could probably, like I said, safely assume it's going to be a weak one. And that also will dictate how you will solve the problem, but it's a strong acid or a strong base versus a weak acid or a weak base. So here are some of our strong acids there. And once again, they do break apart. So since water is involved here, each of these are going to donate an H plus over to water. That's going to generate our H3O plus in this case, since we do have it, and our Cl minus. This will donate over, make our H3O plus, and our nitrate. This will donate over, make our H3O plus, and our perchlorate. And the last one there, kind of hiding, I'll put it up here a little bit higher, H2SO4 plus the water. Again, going to donate its H plus over, going to make H3O plus and HSO4 minus in this case. So each of these are strong acids, which means they're strong electrolytes, which means when you have a solution of these guys, they are going to 100% break apart. So if you had just a solution of hydrochloric acid, which once again is a strong acid, you will have none of the HCl units together. You pretty much will have just a bunch of H pluses in the solution and Cl minuses in the solution. And this is why it is considered a strong acid, because essentially all it has to do is go for a swim. It's going to generate a lot of H plus in that solution really quick. And obviously, as we talked about, H plus concentration will go up, OH minus concentration will go down, and the pH will go down as well, again, because as the H plus concentration goes up, it becomes more acidic, and the pH then will start to drop because of that. Questions on that there? Now, weak acids, on the other hand, are weak electrolytes. And again, you do see these arrows heading in both directions, which obviously we know is a reversible reaction. In each of these cases, H plus is going to be sent over by the acid. And once again, we're going to get H3O plus because we do have water in our dissociation. And that's going to give us F minus. This is going to get us H3O plus and NO2 minus. Going to get us H3O plus and SO4 2 minus. And you can give us H3O plus and a little hydroxide in this case. By the way, just a reminder, obviously, what we're really looking at in each of these equations are these acids dissociating or breaking apart in solution. You can just as easily eliminate the water in the equation, and you could write the dissociation that looks like this. Once again, we see we get our H plus versus our H3O plus as we eliminate the water in the reaction. So again, you can write it like that. Like I said before, pretty much if it's not one of those 6, it's probably going to be a weak acid. And again, just kind of knowing those 6 that are strong acids, it's a good way to kind of know that perhaps these things are weak acids. Now, strong bases, on the other hand, mainly come from group 1 and group 2 on the periodic table. Once again, if you kind of go where lithium, sodium is, you go to potassium, hang a right-hand turn there to calcium, maybe down to strontium and barium. If you hook any of these guys up with some hydroxide, you most likely are going to make some strong bases. Alkaline means basic, and again, those are our alkali metals and our alkaline earth metals, so that is basically the forerunners to basically all of our strong bases. Just like our strong acids, when you have a strong base, it's going to 100% break apart into ions. It's a strong electrolyte, and that's also why it is a strong base, because when something like sodium hydroxide goes for a swim, it is just going to fall apart into ions, and it's going to generate a lot of OH minus in that solution very, very quickly. It doesn't have to do much to produce that OH minus other than basically go for a swim in there. Once again, that's going to cause the OH minus concentration to rise. The H plus concentration will drop, and your pH will go up as it's going to become more basic in that case. And obviously up here with our weak acid, if you had a solution of HF and you tossed it in there, you would actually have a lot of HF units still together, but will break apart a little bit into those ions. And this is why it's still considered an acid, because it still has the ability to produce H plus in solution. It will not produce anywhere near the amount of H plus the strong acid will, but it's still able to produce some free H plus, which still makes it an acid, but it will mainly stay together, that weak acid. Now, as well, we can have some weak bases that are uh, weak electrolytes as well. And since these are bases, it's going to actually accept the H plus from the water, and it's going to produce, honestly, where it comes from. So this reaction will produce where it came from. The F minus came from HF, and it will reproduce it, and it will produce hydroxide in this case. And again, this is why it's considered a base. Same deal, going to send our H plus over there, going to produce our nitrous acid there, and a little hydroxide action in there. Same idea, these weak bases have the ability to produce some hydroxide, so they're still considered bases. The deal with these guys is they pretty much need to do a little bit of work to produce the hydroxide. They gotta go find something like water and do a little reaction to produce that hydroxide, which makes them a much weaker base than something like sodium hydroxide, which is essentially carrying the hydroxide with it and just ready to let go of it when it goes into the solution. So that's why, again, it's a much stronger base, something like sodium hydroxide. It doesn't have to kind of go through all that sort of work. Now, a couple of relationships that's really important to get a handle on is this. The conjugate base of a strong acid is going to be relatively weak. And H3O is the strongest acid that can exist. And a OH minus is also the strongest base. But really, the most important thing here is the relationship between the acid and its conjugate partner. And so the relationship is basically an opposite relationship. If something came from a strong acid, its conjugate partner, either a conjugate base, would be relatively weak. Now, if it came from a weak acid, its conjugate partner will be relatively strong. So there's sort of an opposite relationship here. So if you have an acid, you would have a conjugate base, the Bronsted-Lowry definition. And if that acid was strong, its conjugate base will be weak. And if the acid was a weak acid, its conjugate base will be relatively strong. And we have the same sort of relationship for our base and conjugate acid. If it is coming from a strong base, its conjugate acid will be relatively weak. And if it's coming from a weak base, its conjugate acid will be relatively strong. So that's a really important sort of opposite relationship that comes up a lot in acid-base chemistry, is that if it comes from something strong, it's going to be weak. If it comes from something weak, it's going to be strong. Now, what do we mean by weak and strong? We're going to talk more about this, obviously, in this chapter. But just to sort of preview, what we're talking about is if you create a conjugate base that came from a strong acid, as it's floating around in that solution, it is actually going to be relatively neutral. It's not going to really continue to react. So, for example, if you had a beaker of hydrochloric acid, which obviously is a strong acid, would break apart into H plus and Cl minus. Now, this HCl is a strong acid. This would be its conjugate base, which means it's going to be relatively weak. So when you have this in solution, you're going to have a bunch of Cl minuses and H pluses floating around. The deal is these Cl minuses are simply just going to float around. They're not going to react with anything. They're not going to continue to react, and they're not going to affect the pH of that solution because essentially they're just going to kind of hang out, almost like a spectator ion, just kind of hanging out there, floating around, not really doing much. Now, if you take a weak acid, like our friend HF, which is hydrofluoric acid, and it breaks apart into H plus and F minus. This again is our weak acid. This will be our conjugate base. Now, what happens though when you have, for example, some of this, and most of it will stay together, but if you have some H plus and F minus, that F minus is going to be relatively strong. And what that means is, as we will talk about a little bit later on this chapter, it actually can continue to react with water that's also present in the solution. So even when you produce that, it has the ability to continue to react with water and actually affect the pH. And it can react with water actually just like we see here at the very top, doing this reaction right here. And what it's able to produce, as you can see, is it is able to actually produce hydroxide in that solution. So because the F minus comes from a weak acid, it's going to be relatively strong in the sense that it can continue to react with water. It actually will be able to produce some more hydroxide, and it actually will make the solution in certain cases, if you have this in the salt form, it will make it more basic because it's able to produce some hydroxide in there. And that's what we mean by strong. F minus, for example, is nowhere near a strong base like sodium hydroxide, but is strong in the sense that can continue to react and have an effect on the pH. Same thing with down here. If you have something that comes from a strong base, its conjugate acid will be relatively neutral, won't continue to react. But if it comes from a weak base, it will be considered relatively strong and have the ability really to react with water and do a bunch of reactions we'll talk about, which are known as hydrolysis reactions, and basically can affect the pH of that solution. Any questions on that? Here's a table similar to one in your book, and it shows that opposite sort of relationship. We have strong acids up here on top, kind of our six, kind of missed some. And again, as you go down, going to be weaker acids. And as the strong acids are up on top, weaker bases over there, and stronger bases on this side, weaker acids on that side. So again, that sort of opposite relationship that occurs. Now, when we have a strong acid versus a weak acid, and we want to know the pH of a solution, if you are given the concentration of a strong acid or a strong base, you can figure out the pH of that solution by thinking about what you need to calculate that. So let's just say we were given a strong acid and we wanted to know the pH, right? So something, for example, like HCl, which again is a strong acid, will 100% break apart into H plus and Cl minus. And remember that if we wanted to calculate the pH of it, pH is equal to negative log of the H plus concentration. That means that we need to know what this guy's concentration is. If you remember molarity and stoichiometry, this is, for example, a 1-to-1 relationship between the whole thing and the H plus. So if this happened to be like 2 molar, the H plus concentration would be 2 molar here because it's a 1-to-1 relationship. Also, it's a 1-to-1 relationship between that and the chloride. The chloride concentration in the solution would also be 2 molar. Not that it's important for pH, but that again is how it works. So you can kind of do a mole-to-mole relationship to figure out what it is. The good news, though, is most strong acids are monoprotic, which means they only have one hydrogen, which means if you know the concentration of the strong acid, you actually know the concentration of the H plus. and that will allow you to go right into the pH equation without having to worry about it. Now, if you had a strong base, kind of the same idea, and you wanted the pH, you could look at something like, say, sodium hydroxide here. And because sodium hydroxide is a strong base, it's going to completely break apart into sodium ion and hydroxide ion. And once again here, pH is minus the log of the H plus concentration. Since it's a base, we really don't have H plus here, but we do have hydroxide. And if we could get the concentration of hydroxide, we could actually calculate our pOH from that. Then obviously we can get the pH probably simply by subtracting our 14 from the pOH, and that's probably the best route. Same idea here. If it's like a 1-to-1 relationship there between the whole thing and the hydroxide, that will give you the hydroxide concentration. So sometimes you may not be given just a generic H plus or OH minus. You may be actually given a formula for an acid or a base, and if you see that acid is either a strong acid or the base is a strong base, you basically can get the H plus concentration or the OH minus concentration to calculate your pH. Any questions on that there? All right, so why don't you try then here? All right, so for each of these, both strong acid and strong base here, why don't you calculate the pH of each of these solutions? Okay, so let's take a look. So once again, we have the pH of 2 times 10 to minus 3 molar nitric acid. Again, knowing those kind of 6 strong acids we saw earlier, really important. Again, that is on that list there. So nitric acid is right there on the list, along obviously with our H2SO4, our perchloric, our hydrobromic, and our hydriodic acid. So again, I see that strong. What that tells me is a strong electrolyte, strong acid. It is going to 100% break apart into ions in solution. So it'll break apart into H plus and NO3 minus. Again, if you wanted to include the water on the left-hand side, you would end up with H3O plus on the right-hand side. Same deal, whichever way you want to do it. It's going to be 100% what we got going on over here. And since we do know that the concentration of the whole thing here is 2 times 10 to the minus 3 molar, it is a 1-to-1 relationship, which basically means you multiply the concentration by 1, which keeps it the same. And it would be 2 times 10 to the minus 3 molar. Again, it would also be the same concentration for the nitrate. Just to show you, in case you're not 100% sure why we do that, if you take the concentration 2 times 10 to the minus 3, convert it into moles per liter, which is what molarity is, and you do this long calculation here, in mole-to-mole relationship, it's a 1 mole to 1 mole relationship, 1 mole of HNO3 on the bottom, 1 mole of H plus on the top. Going to multiply and divide. The moles of HNO3 will cancel. We'll leave us with 2 times 10 to the minus 3 moles per liter of H plus. That's the long version of multiply it by the coefficient, basically, is what you're doing. When you multiply it by the coefficient, it's basically stoichiometry. So since that is the H plus concentration, that really is all I need to go into my pH minus the log of 2 times 10 to the minus 3. I'm assuming this probably should give me an acidic pH since this is an acid. And something like 2.7 would be our pH, which is acidic, which is good in this case. Any questions on that one there? On the second one, this is a base. It is probably a strong base, as most strong bases actually have hydroxide in the formula. And it also, if you look again on the periodic table, it is right there as we come this way and down, right there in group number 2, where we will have some of our strong bases made. So once again, that means that this thing is going to completely dissociate into ions. So completely break apart into a barium ion, and we will actually get 2 hydroxide ions in this case. Now, when we look at the concentration here, we are going to be looking for the hydroxide concentration, as that's going to allow us to get to the POH. This is 1.8 times 10 to the minus 2 molar. In this particular case, it's a 1 to 2 relationship. So if you want the correct concentration for hydroxide, you do need to multiply it by 2. And that would be 1.8 times 10 to the minus 2 molar. And that will give you the proper concentration here of 2 times 1.8 to the minus 2, 0.036 molar. Remember, though, that this is not the H plus concentration. This is the hydroxide concentration. That's going to get you a POH that is minus the log of the OH minus the log of 0.036. That's going to get us, I hit the right button and might get us something. Let's see. Gets us a 1.44. If by some chance you thought that was the pH, that should definitely not make sense to you since this is a base. So to get to our pH, we'll do 14 minus the pH, or the POH. And 14 minus the POH here going to get us to a 12.56 pH, which does make sense as this is basic. So I would say probably in the strong base region, especially obviously those from group 2, is probably the one place where you might have to adjust the hydroxide concentration because you probably will get more than one hydroxide given off to you. Any questions on any of that there? So again, if you're given a strong acid, strong base formula, you basically just need to get the H plus, OH minus, and then into the appropriate equations to calculate the pH. Any questions? All right, good stopping place actually, so we'll lay it up there.